think that's working now. I assume it is. All right, now, so what we said we would do today is we're going to run through triglycerides for the benefit of everyone, and anyone that's not even here can look at it. Now, if you are following, so just to clarify, we have got another lesson in SEPTA. So the precursor to triglycerides, I said, was esters. All right, so the assumption is that you know a little bit about the structure of an ester. We've done that already. So we've worked out that an ester, from our previous lesson, is made up of two things. So we have got a carboxylic acid part to the ester, and we've got an alcohol part from the ester. Now, if we just jump forward over to the triglycerides, what we find for the triglycerides is that this is basically a triester. So it links nicely with the previous topic that we did. So really it's basically a triester. And the general formula for a triglyceride, known as fats or oils, is this. Now, these carbon chains, I might add, okay, are up to about 18 carbons long. You can look in your textbook on page 284, and if you look at, for example, the stearic acid, all right, stearic acid has got a formula of CH3, CH2, there's 16 of them, and then a COOH. So it's got 18 carbons in a very, very long carbon chain. So if I've got the fatty acid in this instance being a very long carbon chain, okay, that's the sort of stuff that we get in animal fat. And we look at that from the view of being a saturated fatty acid. The other part of our triglyceride, obviously, is our triol, okay? And the triol here is glycerol. So it's 3 carbons. So if I were to take every one of these alcohols and react it 3 times, okay, with 3 fatty acids, I'd end up with a triglyceride. Now these are naturally occurring anyway, but I can, you saw it in the video before, you can make any fat at the end of the day that you want to. All you need to do is work out what I want on the chains for the carboxylic acid. So I can have longer chains, shorter chains. I can have some of the chains that are unsaturated. So by unsaturated, what we're saying is, fairly obviously, that there is at least a double bond, one double bond, somewhere along this chain, or this chain, or this chain, or all 3. Okay? We'll get to that shortly. All right, so that's the idea, the general structure for the triglyceride. All right, any questions about that one? Is everybody okay with how a triglyceride functions and how it works? We haven't talked much about how it works yet, but the general structure for a triglyceride. All right, now one thing we didn't cover the other day was what we called hydrolysis, did we? So when we looked at esters, we said that if we're going to make an ester, okay, if I were to split this in half, I have to have a carboxylic acid. That would be my carboxylic acid to produce this ester. And I also said I would need to have an alcohol. In this case here, that would be my alcohol. And I react those together. We said it's an equilibrium reaction, and I'm going to end up with this ester here, plus water will be a byproduct. Now, I can actually reverse the reaction 2 ways. I can carry out hydrolysis of an ester using water. That's called acid hydrolysis, believe it or not. Or I can do hydrolysis of an ester under alkaline conditions. And I'll show you with a simple ester, and then we'll do it with a triglyceride. So if I were to take the ester and carry out hydrolysis on the ester, let's spell that right, HYD, hydrolysis, get it right. If I were to carry out hydrolysis under acid conditions, and hydrolysis just is simply reaction of anything with water, we come across that term before when we did alcohol, do you remember? There were 3 equations. The first one was a complex carbohydrate going to a disaccharide, that was hydrolysis. Then it was a disaccharide going to a monosaccharide, which is sugar, and then it was the reaction of the yeast with the glucose to produce alcohol. The first 2 steps were actually hydrolysis reactions, and people sometimes overlook that. All right. Anyway, this one here, so I can actually take my simple ester structure and if I react it with water, okay, I end up with the following. I end up with a carboxylic acid, and I end up with a straight alcohol. Nothing really surprising about that. So hydrolysis of an ester under, okay, acid conditions just with water, okay, will give me the carboxylic acid and the alcohol back again. Can also undergo hydrolysis under base conditions, and this is a little bit different. We know that this is reversible because we just talked about it in our formation of an ester. Whereas this one here you'll see is not reversible. So if I take an ester, and if I react the ester with sodium hydroxide, it's a one-way arrow, it's not reversible. So we end up with this compound, which is a salt of the carboxylic acid. We call this a carboxylate salt. So a carboxylate salt, plus I'm going to end up with, what's the other product going to be? Plus, good, we're going to end up with the alcohol. Alright, here's the other product of that reaction. So end up with the salt of the carboxylic acid plus the alcohol, and it's not reversible. Alright, now if we go over here, and if I were to carry out hydrolysis of the ester, of the triol, in this case, the triglyceride, and we'll link it up to the section on soaps as well. If I were to carry out hydrolysis of the triglyceride, and we'll do it side by side, and hopefully it won't confuse you too much. If I were to carry out hydrolysis of this with water, what are my products going to be? These questions will come up shortly in the book as well. What would I get if that was a structure and I did hydrolysis with water? I'm going to get 3 different fatty acids, 3 different carboxylic acids. These carbon chains could be the same, by the way. They are in the case of sodium stearate. They're all the same. They're all 18 carbons and saturated. Or I can have mixtures, different carbon chains. Okay, some of them saturated, some unsaturated that we'll talk about shortly as well. So if I do it with water, I'm going to get this carboxylic acid here. Or I should be saying fatty acid, shouldn't I? We're going to get this one. And we're going to get this one. So I'm going to actually break off my 3 fatty acids because I know that they're going to break here, and here, and here. That's what we did when we talked about hydrolysis of an ester. We break it at that single oxygen to carbon bond. The other product is always going to be this, every single time. So glycerol, is going to be the alcohol that I'm going to end up producing when I carry out hydrolysis of that ester, okay? Or triester, I should say. Triglyceride to be specific. So they're the 2 products that I end up with, and we know that that's reversible as well. So as you can see, depending on what fat or oil I want to make, I could do it synthetically with 3 different fatty acids, or 3 fatty acids that are the same, doesn't matter. If I do it in the presence of sodium hydroxide, if it's alkaline hydrolysis, as we just said, we end up with these. I would end up with 3 salts, okay? I'd end up with that salt, I'd end up with this one. Now, although in our example here I've got 3 different fatty acids, typically they're normally the same, okay? So I just get 3 of the same, all right, in my reaction. And we do that when we produce a soap that I'll talk about shortly as well. So this one here, Na+, and of course the other product is going to be the same. So it's still going to be that same alcohol again, which is glycerol. That comes back again, all right? So this is not reversible. Now, hopefully nobody's going to sleep, but if I were to do this, okay, we're going to jump forward in the section on materials, okay, in the course, looks at the manufacture of soap, all right? And one of the things we look at is, how do we make soap? Well, we make it like this. Typically, if we're going to make soap, we start off with fat, typically animal fat, but you can use unsaturated fats as well. We react it with sodium hydroxide and we get soap. plus glycerol as my products. Now in the case of a fat, as I said previously, that carbon chain is up to 18 carbons long. All right? So if I were to show you, saponification is the word that we use if it's hydrolysis of a triglyceride. Alkaline hydrolysis of a triglyceride is called saponification, obviously because it makes soap. All right? It would look like this. So if I changed, actually I'll do the actual reaction and you'll see the difference. So if I were to make this, all right, a fat, and our equation for the stearic acid, so let's assume that we're using the stearic acid, it would look like this. We've got CH3, CH2, 16, so that would be that in blue, that's my blue. All right, CH2, CH3, 16, and then that would be the stearic, okay, acid part of my triglyceride. They'd be the same, CH2, CH3, 16, and continued on the same thing, CH2, CH3, bracket 16. Now if I did alkaline hydrolysis of a fat, just animal fat, you can do that at home, all right, if you like balling up fat and lard, it's exciting stuff. All right, and a bit of sodium hydroxide, we end up with this. The product of this is still exactly the same, i.e. we still get this triglyceride, or this triol here, as I should have said, and we end up with 3 of these. We end up with 3 CH2, CH2, 16, CO, minus, Na plus. This stuff here, Jack, CH2, did I say, no, that's my bad, alright? So there should be CH2, you've got to run that away, Jack, alright? So these are obviously CH2s on the carbon chain, alright? 2, 2, 2, that should be 3, 3, 3, okay? So if I were to draw it, I won't, that goes, obviously it goes 1, 2, 3, 4, 5, 6, blah, 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 alright? So the end one is going to have CH3, that's why it's CH2, just short version of the structural formula. You got the idea, right? So, this is my structure for soap. This compound here, alright, is the soap. Now, we won't go into today how the soap works, but from year 11, it is a long carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, all right? And I think, so if we go there, C1, O minus 1, 2, 3, 4, 5, 6, 16, the bottom, 17, 18, that's it. So that there, all right, is my general formula for soap. Now, if you remember to what we talked about or seen previous in the video, all right, this now is a polar part to a molecule. This is a non-polar part of the molecule. We go back to the idea of like dissolves like. So soap works by dissolving dirt or grease in water. And so the grease is non-polar, and so what happens is the soap molecules surround all the grease particles with the actual, what's that called? Is it called hydrophilic? That's a frighten of water, doesn't want to go to water at all. So the hydrophilic ends, the non-polar ends attract to the non-polar grease. So if you can imagine a sphere, lots of them though, not just one big one in the wash, but many, many billions of these things. And each sphere has got a grease particle or something non-polar in the middle, but on the outside, the water sees this, and the water says, it's just a negatively charged compound. I can iron dipole bond with that, and the water is tricked into thinking that grease is actually polar, but it's not. It's shielded on the inside, all right, of a sphere. So the concept of forming a micelle we'll go into a little bit later. All right, in terms of other things that we need to look at outside of that, we haven't talked about it yet, but we did a little bit at the beginning because, and we're just waiting for Jack to rock up, weren't we? Now we can do it in a bit more detail. Has everybody got that down? It's going to get gone anyway, alright? So we'll get rid of that. And what we want to do now is to look at some of the reactions of the triglycerides and how we can actually change a liquid into a solid. Okay? Alright, now, we forgot, get rid of that, put that back again. Alright, now, fats and oils. Hopefully you can recall, again from what we talked about before, is that fats typically are found in a solid form, okay, and oils typically are found in a liquid form, although very viscous, okay, depending on the carbon chain length. And the thing was, why are fats solid and why are oils liquid? Okay, stacking, yeah, all right. So if you can imagine, and I'll actually just draw a fat structure over here, but I'll do it a little bit smaller so you can sort of get the idea. The picture is much better done in the book than what I can do. Get that right? Okay, now, let's assume we're talking about animal fat. Who's got grandparents that have got a lard bucket? Have you ever seen grandparents with a lard bucket? It's not our generation. It was maybe my generation, okay? But what my grandparents used to do is that they cook a roast, okay? And then they take the fat and they pour the fat into normally a tin, okay? There's a lot of flavour in the fat, okay, the animal fat. And then they put it in the cupboard and they let it, okay, cool down. And the next roast they had, they get a big spoon, they take the fat out and they slap it on top and rub it all over the top, okay, because they were trying to transfer the flavour over. It's probably not good for our cholesterol, okay, because, Jack?
They also, I've seen that more so used for the creation of a form of gravy.
Exactly, all right. And it's a great base to make really nice gravy. So you can see what it does. Exactly, all right. So, unfortunately, or fortunately, I don't know which way it is, all right. So, saturated fats are typically solid, and you would know that because if you cook anything, does anybody cook in here? Okay. You've only got to go to your barbecue plate after you've had, say, some sausages, come back, you know, a few hours later, and then open up the barbecue, and you'll see that there's this layer of fat on the plate.
Actually, they
solid.
With a lot of those, they actually drain into a bucket right underneath it.
Exactly. Or look in the bucket. Okay, in our school barbecue, all right, it's got a big drain bucket, and what's in there? Solid fat, typically. Anyway, why is it solid? Well, as Jack said, they sort of do this, okay, the chains pack together. What sort of bonding happens in a long carbon chain? What sort of bonding? Dispersion is what we're after, okay. So if we would look at this long carbon chain, alright, hopefully you can see that if it is saturated, it's got to be saturated, then all of these chains, if that's one fat molecule, and I can get another one and put it along there as well, okay? So along the entire length of this saturated fatty acid, or saturated triglyceride, hopefully you can see we can get dispersion forces all the way along the chain. So it just makes sense that these compounds are going to be solid at room temperature. They're going to be held together much better. They're going to be stacked together like bricks, if you can imagine. One here, one here, one here, one here, etc. So they're certainly going to be solid at room temperature. That's what we'd expect. However, if we change it, all right, and same structure, but we'll turn it into an oil, and then we'll talk about how to take an oil into a fat. It seems a bit stupid, doesn't it? Right. But it actually happens, simply from a not cosmetic, what's the word? Consumer's demand. Okay, we'll talk about that in a minute. Alright, so if I do this, if I've got a carbon chain and it has one double bond in the structure, doesn't matter where it is, okay? And I'll just do this again over here. okay, and this can go in all directions like that, okay, and it'll keep on going, could even cross over the other chain, I'll keep on going again here, same thing, and I've got, say, it's just a little bit different this time, that can start to branch out, and there's nothing at all, okay, there's nothing at all forcing these chains to be together. So automatically, as soon as I have an unsaturated site, and it doesn't have to be in, yeah, sort of like that. It's like somebody's got arthritis with their fingers, yeah? Yeah, it's pretty ugly stuff. So, bearing in mind, all right, that at this particular site here, if we expand that site, okay, we know, all right, that at that particular site, this is actually what's happening. Because there's 120 degrees here, 120 degrees here, and 120 degrees there, okay? And there's nothing that causes, well, there is some reason, but what you'll find is that these will branch, we call it branching, in different directions. And as soon as these branch in different directions, we may have some dispersion forces here, we might have some there. Thanks, just need to listen, boys. But the far or vast majority, okay, of this carbon chain is in no man's land. There's no reason why this carbon chain can dispersion force to that one. It can't get close enough to do that. And so, in effect, it's like getting a whole lot of unusually shaped structures, because they won't all be the same shape, and trying to get the shapes to blend together. Okay, and as you saw previously on that video, all right, that it's pretty hard to get all these bent chains fitting together in any order. Consequently, they're liquid. All right, there's no reason for one oil molecule to get next to another one. All right, the structure doesn't allow it. All right, is everybody okay with the branching and how it impacts the structure? Yeah. Now, they did talk about the fact, and I mentioned it a minute ago, that people that have diets based on, obviously, oils tend to have a healthier outcome, a longer term outcome, all right? They tend to be healthy for you because your body can break these down much more readily. If you've got a saturated site, obviously reactions that occur at that particular site, so you're able to digest them much better. It's better for you. Saturated fats, on the other hand, are fairly unreactive. Anything that's got single bonds on single bonds and single bonds, it's very hard to get anything to come and react to that. So therefore, we talk about the problem with saturated fat, although if you do some research right now, all right, the theory now is that they're not, okay, as bad for you as what people first think, okay, or thought, I should say. It's about in moderation, all right? So you do need to have saturated fat in your diet, as we said, all right, one saw in the previous video. If the saturated fats provide some of the essential fatty acids, the essential fatty acids are used for what? Biologists, what do you? Yeah, energy and making certain types of proteins that your body needs. Okay? So if you're missing certain fatty acids in your diet, okay, you won't be able to produce certain types of proteins, enzymes, etc.
If you have too much.
That's another story. Okay? It's like everything else. If you do things in excess, it tends to have a negative effect. All right? Yes?
Is cholesterol caused by too much, high cholesterol, is that too much saturated?
Saturated, but it also can be a genetic factor.
Okay, yeah.
So if you've got a history of high cholesterol in your family, it tells, basically it's an indicator for a physician to say, wait a minute, it's probably something to do with genetic makeup and how your body deals with saturated fat.
Yeah.
Some people I know that are always skinny, doesn't necessarily mean they've got good cholesterol, it could be bad cholesterol, but it just simply means that they can actually seem to process or digest at a much quicker metabolic rate. It's genetic, we're all different, okay? But I need to do more research on that one. I couldn't give you the exact answer for that, maybe. All right, so liquid solids. Now, back to this. So we're talking about this as being a better diet, all right? So if you look at, for example, Western world, If we lived on a diet of meat and saturated fats only, not only do we tend to sort of grow around this area, all right, we have all sorts of issues with heart disease, high blood pressure, etc. Because normally going with this is a high salt intake as well. But obviously, in terms of people that have got a high unsaturated oil intake, they tend to be healthier. Minimal heart disease, so a Mediterranean diet, they call it, all right, around the Mediterranean, okay, where they have got lots and lots of oils, particularly olive oil, healthy. Why? It's unsaturated. The problem with consumers, and where consumers is that it's very rare that you'll get people that have been, you know, brought up with like spreading something on toast. It's a solid. I haven't seen people go to the cupboard and get olive oil and pour on their toast. Has anybody do that recently? Maybe some of your parents, grandparents might do that, depending on your ethnic background. But certainly it's not common. All right. So Western culture says we like to have something that's solid that we can spread on toast. Okay. So what we do is this: we use chemistry to make everyone happy. All right. So we actually take this unsaturated oil and we carry out a process where we add hydrogen. It's called hydrogenation. It's done at high temperature and pressure. And we transfer these unsaturated into saturated. And so we begin to straighten the chains, but we don't straighten all the chains, okay? Because if we did, we might just go back and have saturated fat. All right, so we talk about the polyunsaturated ratio. You've heard of things like polyunsaturated margarine? No? Look at the labels and it will say the polyunsaturated ratio is 2:1. Okay? So that's an indication of how saturated the margarine is. Because if I add lots of hydrogen, it's going to be largely saturated, not good. Poly means many, unsaturated. So we really want to have a significant number of sites in the triglyceride that are unsaturated. We don't want to make it back into butter again necessarily. So margarine
is just unsaturated.
It starts off with actually normally it's like sunflower oil, okay. Or what are the yellow crops? Canola oil, okay. It's typically the source. Although you'll get olive oil margarine now. That's all around. It's been around for a while. Look at it. Go shopping.
So
okay.
Margarine is the unsaturated.
Margarine, the source of margarine is always typically a vegetable oil, normally from a plant. Okay? But it's a liquid. Alright? So in industry, industrial chemistry, we take the liquid, we actually carry out a process of hydrogenation under controlled conditions, and we produce margarine. We haven't gone all the way to butter. It is not totally unsaturated. We stop. We stop halfway through. It's a stoichiometric ratio, obviously. Okay, knowing about stoichiometry and reactions. And so we add a portion of hydrogen based on a portion of the original oil, depending on how saturated we want the end product to be. Everybody got that? Okay. So all we're doing is an addition reaction, and we've touched on this before. Yep. So if I was going to do an addition reaction, if I add hydrogen, okay, to a double bond, and we'll talk about testing in a minute. How do I test how saturated or unsaturated the margarine is? We can do that in the lab. Okay, if I do that, I'm going to turn something that was originally unsaturated, okay, into a saturated form because the hydrogen adds across the double bond. If I change the colour, hopefully you can sort of see where that's on. Alright? So that's just an addition reaction. So through addition, along the chain, we can turn it into a solid. Now, what do you know about margarines if you leave them open, if you leave them out in summer? They go back to, they've got a very low melting point. And that's the other reason why people like them, because you can get them out of the fridge, okay, and they're not like solid. Whereas if you get butter out of the fridge, okay, it's got a slightly higher melting point, all right? But if you put margarine in the fridge, it's obviously got a low melting point, it's still soft, okay? So we still have an advantage, just a consumer thing, all right, that it's got a much lower melting point because it's got some sites of unsaturation. It's not totally unsaturated. All right, questions about that one? Mason?
You know how like for fries, I like the oil becomes as like a solid.
Yes.
And then when you heat it up, it becomes a liquid.
Correct, yeah.
So why is it solid? Like, is it oil?
I can only use, well, if you look at the oil in fries without knowing, okay, where the shop is, you have to ask the people what sauce are they using. Okay, what sauce are they using? All right, turn that off, shouldn't I? What sauce are they using for their fat when they're doing the frying? Because some shops will be very proud about using unsaturated oils. They put it in their window that we're using unsaturated oils to do our cooking, whereas other people won't advertise the fact that they've got animal fat in their boilers and they're not worried about the outcome for you. All right, because it's probably cheaper. So if it's a solid, it could be like in a margarine context. It could be partially saturated, but not totally saturated. Yeah. And I think you'll find that most of the fish shops these days, I don't know what, do you do fried stuff at the shop? Yeah. Okay, so you need to ask the people what oil they use. I'm not up with that either. All right. What was the heading? All right, testing. All right, so if I can get you to have a look at page 267, another part of this section here, again, is critical, all right? Now, as I said, we can test the degree of unsaturation, all right, within a oil. We can actually do a reaction to work that out. And hopefully you can work out that if I've got a chain like this, for example, if that was somewhere on the carbon chain, if I actually add bromine, by knowing the number of moles of bromine that's consumed by that reaction, I can work out the degree of unsaturation. So if it consumes only 1 mole of bromine, I would end up, okay, with this. So if the bromine added across that double bond, okay, I could work out the moles of bromine that reacted, but of course it's not going to add across one, is it? It's going to add across both. So we can actually determine how unsaturated a chain is by knowing how many moles of bromine, or it could even be iodine. I think the book uses a number for that, and the number they talk about, where is it? Just got to find it. So they talk about a number and they say, here it is. The iodine or bromine number of a fat or oil is the mass of iodine or bromine. It's on page 289, halfway down. That reacts exactly with 100 grams of the fat or oil in relative terms. The greater the value of the iodine or bromine number, i.e. the more that reacts, the greater the degree of unsaturation. That's obvious, I think. All right? So if it's got more saturated bonds, the iodine or bromine number will be greater, which means more of it's reacted, which means there's more unsaturated sites on the long carbon chains. And we call that the iodine or the bromine number. All right, now, what else do we need to do? Apart from, we've covered hydrolysis, you could have a look at page 286, and it talks about the percentage of saturated versus unsaturated fats. For example, beef fat, it's not all bad, okay? It talks about saturated fats, 55%, and 45% unsaturated. So they always say that protein in your diet in terms of animal meat, okay, is good. Pig fat, 45, 55. If you go down to coconut oil, saturated 95, unsaturated 5. As my wife always says, we're making a nice curry, all right, although you do add coconut to it, all right, we actually add coconut milk or coconut cream, but if I were to cook in coconut oil, you can see that it's probably not the healthiest thing to do. Yeah, it's exactly. It's contrary to what you would expect. Like chemistry, you do everything, and then we say, here's the rule, but here's the exception to the rule. Okay? So here is a plant material. Coconut oil is predominantly saturated, but yet it's a liquid. Okay? And
So it's more like it's not exactly a liquid, it's more like solid.
if you go and buy coconut oil, I might add, it's not actually liquid, Will. It's a solid. It comes normally in a jar, and it's white solid. You guys probably know that. You use coconut oil? Yeah. All right. So coconut oil, it looks like a big lump of lard. It's solid. It's not liquid. All right. So even though it's in the category of an oil coming from a plant. All right. That's the only reason why we call it an oil. But it's not a solid at room temperature. Oh, sorry, it's not a liquid. It's a solid. You've got to dig it out to get it out. Okay. And you'd use it like minimally. It's not something that you'd sort of use a lot of. All right. Any general questions about that? So triglycerides hooks up with esters that I've just got rid of. It's got a link with the degree of unsaturation to saturation. It's quite relevant. So we're talking about oils, cholesterol levels, okay, and fats. One thing I didn't mention, just remembered, and you can research this. Have you heard of the term cis and trans fats? Cis and trans? Maybe you haven't. Okay. So I've got an article attached, I think, to the next lesson in sector. So if we're looking at a structure like this, this is called a trans structure. It's like opposite on the opposite sides. I forget which one. Is it the trans fats bad for you, the cis? Forget which one it is. That one. So if a structure, all right, is in this sort of a format here, all right, this is a trans version. I'm talking about the isomers. I mean, we've actually talked about isomers in year 11, all right? So the same formula, different structure. So I can actually bend these are carbons, all right? This is an example of a cis structure. And so depending on the structure of those, not in the course, of course, on the course, of course, all right? But if it was, one of those is bad for you. I think it's the trans fats that are bad for you, but I don't really know why. But you can look it up in that article that I've attached to the lesson. Okay? All right, I think we will leave it at that and we'll get into some questions. All right?